Elon Musk says we'll have humans on Mars by 2030. NASA says maybe 2040. They show you beautiful animations of rockets landing on red sand, astronauts planting flags, colonies rising from the dust, and everyone nods along like it's inevitable, like it's just a matter of time and money. But here's what nobody's telling you. When you actually do the physics, when you calculate the radiation, the distances, the energy requirements, the biological limits of the human body, you don't get a plan. You get a death sentence. I'm not saying it's difficult. I'm saying there are problems we don't know how to solve, problems that might not have solutions, and I want to show you exactly why. Let me tell you something about distance that most people don't understand. We say Mars is far away. We hear numbers like 140 million miles, and we nod, because big numbers are just big numbers. They don't mean anything visceral to us. Our brains can't process them. So let me try to make it real. When you drive your car across the country, coast to coast, Los Angeles to New York, that's about 2,800 miles. A long trip takes you maybe 4 or 5 days if you're pushing it. You get tired. You stop for gas, for food, for sleep. The journey feels significant. Now imagine doing that trip 50,000 times. Back and forth, 50,000 round trips across the entire continental United States. That's the distance to Mars. Not at its closest approach, mind you. At its closest, Mars is about 34 million miles away. At its farthest, it's over 250 million miles. The 140 million figure is just an average, a number that hides the brutal reality of orbital mechanics. And here's the thing about space. It's not like driving. On Earth, you can stop. You can turn around. You can pull over if something goes wrong. In space, once you're going, you're going. There's no pulling over. There's no turning around. At least not without spending enormous amounts of fuel you don't have. You're committed. The moment you leave Earth orbit, you're on a trajectory that will take months to complete, and there's nothing you can do to speed it up significantly. The fastest trip to Mars, using current technology, takes about 6 to 7 months. That's with everything going right. That's with optimal orbital alignment, which only happens every 26 months. Miss that window, and you wait 2 more years. Or you take a longer route that could push the journey to 9 months or more. 6 months. Think about what that means. 6 months in a tin can, hurtling through the void. No grocery stores, no hospitals, no rescue missions. Everything you need to survive, every ounce of food, every drop of water, every breath of oxygen, you bring with you, or you make yourself. And if something breaks, if something critical fails, you fix it with what you have, or you die. Nobody's coming to help you. Nobody can. But distance isn't even the hard part. Distance is just context. The real problems start when you look at what's filling that distance. Space isn't empty. I know that sounds contradictory. We call it space. We call it the void. But it's not empty in the ways that matter for human survival. It's filled with radiation. Constant, invisible, deadly radiation that your body has no defense against. On Earth, you don't think about cosmic radiation. You don't have to. The planet protects you. You're wrapped in a magnetic field that deflects charged particles from the sun. You're blanketed by an atmosphere that absorbs what gets through. You walk around every day bathed in protection you can't see or feel. The moment you leave Earth's magnetic field, that protection vanishes. You're exposed, naked to the universe. There are 2 main types of radiation you have to worry about in deep space. The first is solar particle events. These are bursts of high-energy protons that erupt from the sun, usually associated with solar flares or coronal mass ejections. They're unpredictable. They can happen at any time. And when they happen, they're dangerous. During a major solar particle event, the radiation dose can spike to lethal levels within hours. I'm not exaggerating. We're talking about doses that cause acute radiation syndrome. Vomiting, fatigue, hair loss, internal bleeding, death, the kind of thing you see in nuclear disaster victims. Now, these events are relatively rare. They don't happen every day, and they have a spectrum of intensity. Many are minor, survivable with adequate shielding. But the big ones, the once-in-a-decade events, those can kill you. And on a 6-month journey to Mars, the probability of encountering a significant event is not negligible. The second type of radiation is worse in a way, because you can't hide from it at all. It's called galactic cosmic radiation, GCR. These are high-energy particles, mostly protons and heavier nuclei, that come from outside our solar system, from supernovae, from distant catastrophic events. They've been traveling for millions of years, and they carry enormous energy. GCR doesn't come in bursts. It's constant, a steady drizzle of atomic bullets passing through everything. And when I say everything, I mean everything. These particles are so energetic that they pass through spacecraft walls like the walls aren't there. They pass through your body. They pass through your brain. When a heavy GCR particle passes through living tissue, it doesn't just irradiate cells the way X-rays do. It physically destroys them. It creates a track of damage, a line of dead and mutated cells. In the brain, this is particularly concerning. We're talking about irreversible neural damage, cognitive decline, memory problems, changes in personality, and we don't fully understand the long-term effects because we've never exposed humans to this kind of radiation for extended periods. The astronauts on the International Space Station, they're still mostly protected. The ISS orbits within Earth's magnetic field. They get some GCR exposure, more than people on the ground, but far less than they would in deep space. The Apollo astronauts, they went beyond the magnetic field, but only for a few days. A Mars mission means months of exposure. Constant, unshielded, unavoidable exposure. So how do you protect against it? The honest answer is, we don't know how. Not really. Not with current technology. Shielding works against solar particle events, at least partially. You can build a storm shelter in your spacecraft, a small compartment with extra shielding, where astronauts can retreat during a solar event. The shielding absorbs or deflects many of the lower energy particles. It's not perfect, but it reduces the dose to survivable levels. But GCR is different. GCR particles are so energetic that conventional shielding doesn't stop them. In fact, it can make things worse. When a high-energy particle hits a shield, it can shatter into secondary particles, a phenomenon called spallation. You end up with more particles, not fewer. The shield becomes a source of additional radiation rather than a barrier against it. There are theoretical solutions, magnetic shielding, where you create an artificial magnetic field around the spacecraft. Water shielding, where you surround the crew compartment with a thick layer of water that absorbs radiation. Hydrogen-rich materials that are more effective at stopping particles without creating secondaries. But none of these exist as practical, flight-ready systems. Magnetic shielding would require enormous power and superconducting magnets. Water shielding adds massive weight, which makes the rocket equation even more brutal. Hydrogen-rich materials are still in development. So right now, today, if we sent humans to Mars, they would be exposed to radiation levels that exceed NASA's own safety limits. Not by a little bit, by a lot. NASA has career dose limits for astronauts. A Mars mission would blow through those limits before the astronauts even arrived. And we're not just talking about cancer risk, which is significant. We're talking about acute effects, cardiovascular damage, immune system suppression, cataracts, and the cognitive effects I mentioned. Astronauts arriving on Mars might have measurably reduced mental capacity. They might struggle to perform the complex tasks required to survive on a hostile planet. This isn't speculation. This is what the studies show. NASA's own research. Studies on mice exposed to simulated GCR show significant neural damage and behavioral changes. Extrapolating to humans is imperfect, but the direction is clear. Long-term deep space radiation exposure is bad for brains. So that's the first impossible problem. Not difficult, not challenging, possibly impossible with current physics and engineering. We need materials or technologies that don't exist, and nobody knows when or if they'll be invented. But let's assume we solve the radiation problem. Let's assume some genius invents a perfect shield that weighs nothing and stops everything. We still have the rocket equation to deal with. The rocket equation is the tyrant of space travel. It's the reason everything about spaceflight is so hard and so expensive. And it's not a technological limitation. It's physics. Fundamental physics that cannot be engineered around. Here's the problem in simple terms. To go anywhere in space, you need to change your velocity. You need to speed up, slow down, change direction. And to change velocity, you need to throw mass out the back of your rocket. That's what a rocket does. It throws stuff backward very fast, and by Newton's third law, the rocket goes forward. But the stuff you throw backward is fuel, and fuel has mass, and you have to accelerate that mass along with everything else. So to carry more fuel, you need more fuel to carry the fuel. It's recursive, exponential, brutally punishing. The equation is simple. It's called the Tsiolkovsky rocket equation, named after the Russian scientist who derived it over a century ago. And what it tells you is this: the amount of fuel you need increases exponentially with the velocity change you want. For a Mars mission, you need a lot of velocity change. You need to escape Earth's gravity. You need to adjust your trajectory for the transfer orbit. You need to slow down at Mars. And if you want to come home, you need to escape Mars's gravity, adjust trajectory again, and slow down at Earth. The total velocity change for a round trip to Mars, using conventional trajectories, is something like 15 to 20 kilometers per second. That's an enormous number. And when you plug it into the rocket equation with chemical propellants, you get a result that's staggering. For every kilogram of payload you want to send to Mars and back, you need dozens, sometimes hundreds of kilograms of fuel. The Saturn V rocket, the most powerful rocket ever flown, was 85% fuel by mass. And that was just to get to the moon, a trip requiring maybe 15 kilometers per second of velocity change depending on how you count. Mars requires more, much more. This is why every Mars mission proposal involves massive spacecraft, thousands of tons at launch, most of it fuel. And we're not even talking about landing, which requires even more fuel, or taking off from Mars, which requires fuel that has to be brought from Earth or manufactured on Mars. The rocket equation doesn't have a solution. You can't engineer your way out of it. You can only make incremental improvements. Better engines that use fuel more efficiently. Lighter materials for the spacecraft. Clever mission architectures that minimize the velocity change required. But all of these are marginal gains. The fundamental problem remains. Getting mass to Mars and back requires an extraordinary amount of energy. And we have to lift all of that energy from Earth's surface, which means lifting it against Earth's gravity, which means the rocket equation applies twice. Once to get off Earth, and again for the actual journey. Every kilogram matters. Every gram matters. You want to send humans to Mars, you need to keep them alive. Life support systems, food, water, air, waste processing, radiation shielding, medical equipment, tools, spare parts. Every item on that list has mass, and every kilogram of mass requires exponentially more fuel to deliver. This is why robotic missions to Mars are hard but achievable, while human missions remain speculative. A rover doesn't need to eat. It doesn't need to breathe. It doesn't need protection from radiation or psychological support during a year-long journey. It just needs power and a few scientific instruments. Humans are heavy. Humans are demanding. Humans are fragile in ways that robots aren't. And the rocket equation punishes all of that mercilessly. So we have radiation, which we can't shield against effectively. And we have the rocket equation, which makes everything exponentially more difficult. And we haven't even talked about the destination yet. Mars is not a backup Earth. Mars is not a fixer-upper waiting for human ingenuity to make it habitable. Mars is a frozen, irradiated, airless desert with an atmosphere that will kill you in minutes. The Martian atmosphere is 95% carbon dioxide. There's almost no oxygen. The pressure is less than 1% of Earth's. If you stood on Mars without a suit, you wouldn't just suffocate. Your blood would boil. Not because it's hot, it's actually extremely cold, but because the pressure is below the Armstrong limit. Below that limit, the water in your body vaporizes. You'd be dead in seconds. The temperature on Mars ranges from about -80 degrees Fahrenheit on a warm day to -200 degrees Fahrenheit at night near the poles. Even at the equator in summer, temperatures rarely get above freezing. And there's no thick atmosphere to hold heat. When the sun goes down, the temperature plummets. The soil is toxic. It contains perchlorates, chemical compounds that are harmful to humans. You can't just plant crops in Martian dirt. You'd have to process the soil extensively, remove the perchlorates, add nutrients, and somehow deal with the fact that Mars has no magnetic field, so the surface is constantly bombarded by radiation that sterilizes the top layer of soil. There's water on Mars, but it's frozen, mostly at the poles, with some subsurface ice elsewhere. Accessing it would require drilling, melting, purifying, all of which requires energy and equipment that has to be transported from Earth. And the dust storms. Mars has global dust storms that can last for months. They block sunlight, which means solar panels don't work. They coat equipment with fine particles that damage machinery. The dust itself is abrasive and potentially toxic. This is the planet people want to colonize. This is the backup plan for humanity. A world where everything is trying to kill you, where the environment is more hostile than anywhere on Earth, where survival requires constant technological intervention. I'm not saying it's absolutely impossible to live on Mars. Given enough resources, enough technology, enough time, humans are ingenious. We might figure it out. But the casual optimism you see in TED Talks and press releases, the idea that we'll have colonies on Mars within a decade or two, that will terraform the planet and make it Earth-like, that's not grounded in physics. That's grounded in wishful thinking. In marketing, in the human tendency to underestimate problems we don't fully understand. The physics says Mars is incredibly hard. The physics says we're not ready. The physics says there are problems we don't know how to solve. And that's what I want to explore in the rest of this conversation. Not to be pessimistic, not to say we should give up, but to be honest, to look at the actual challenges without flinching. Because you can't solve problems you don't understand. And right now, I don't think most people understand just how hard this really is. Let's talk about time. Because time is a problem that people severely underestimate when they imagine a Mars mission. And I don't just mean the 6 or 7 months it takes to get there. I mean everything that follows. When you land on Mars, you're not done with the journey. You're committed to the longest, most dangerous camping trip in human history. And you can't leave when you want to. You leave when orbital mechanics allows you to leave, which means you're stuck on Mars for a long time. The reason is something called the Hohmann transfer orbit. It's the most fuel-efficient way to travel between two planets. You launch from Earth when the planets are in the right alignment, coast along an elliptical path, and arrive at Mars when Mars has moved to the right position to intercept you. The whole thing takes about 6 to 8 months, depending on the specific alignment. But here's the catch. Once you arrive at Mars, you can't just turn around and go home. The planets have moved. Earth isn't where it was when you left. To go home using another Hohmann transfer, you have to wait for the next alignment. And that takes about 26 months. So here's the mission timeline for a Mars expedition. 6 months to get there, then a minimum stay of about 18 months, waiting for the planets to align again, then 6 months to get home. Total mission duration, roughly 2.5 to 3 years. 2.5 years. Think about what that means. For 2.5 years, astronauts would be completely isolated from Earth. Not just physically isolated, communication isolated. The speed of light creates a delay. When Mars is close to Earth, radio signals take about 4 minutes to travel between them. When Mars is far, it's over 20 minutes, each way. That means no real-time conversation, no calling mission control for help, no video chats with family. You send a message, wait 8 to 40 minutes for a response, then respond to that. It's not communication, as we understand it. It's correspondence. Letters across the void. If something goes wrong, mission control can't help you in real time. By the time they see the problem and formulate a response, you've already had to deal with it yourself. Either you solved it or you're dead. The astronauts are on their own, in a way that no humans have ever been on their own before. Now, the psychological effects of this kind of isolation are not fully understood. We have some data from Antarctic research stations, from submarine crews, from the International Space Station, but none of these are truly comparable. Antarctic stations can be evacuated in emergencies. Submarines surface eventually. The ISS is 250 miles from home, with regular resupply missions and the possibility of emergency return. Mars is 140 million miles away, with no possibility of emergency anything. Studies show that long-term isolation causes psychological problems. Depression, anxiety, sleep disorders, interpersonal conflict, cognitive decline. And these are in controlled environments with relatively short durations. A 3-year Mars mission would push human psychology into unknown territory. The astronaut crew would be a small group, maybe 4 to 6 people. They would live in cramped quarters, smaller than a studio apartment, for 3 years. They would see the same faces every day. Every irritation, every conflict, every personal quirk would be magnified by constant proximity and the impossibility of escape. On Earth, if your roommate drives you crazy, you can leave. Take a walk, go to a bar, visit a friend. on a spacecraft, or on Mars. There's nowhere to go. You're trapped with these people, and they're trapped with you. For years, history is full of examples of small, isolated groups descending into conflict, even violence. Antarctic expeditions, maritime voyages, research stations. Put people in close quarters for too long with too much stress and things go wrong. Relationships fracture, trust breaks down. In extreme cases, people have killed each other. We'd like to think that highly trained astronauts would be immune to these problems. They're selected for psychological stability. They're professionals, but they're also human, and no amount of training can fully prepare you for the psychological reality of a 3-year mission to a dead planet with no escape and no rescue. NASA takes this seriously. They've done studies, they've run simulations, but simulations have a fundamental limitation. The participants know it's a simulation. They know that if something really goes wrong, they can leave. That knowledge changes everything. The true psychological burden of a real Mars mission can't be simulated. It can only be experienced. And we haven't even talked about the physical effects of long-term spaceflight. Zero gravity does terrible things to the human body. In zero gravity, your muscles atrophy. Without the constant resistance of supporting your own weight, muscles weaken. Astronauts on the ISS exercise for 2 hours every day using specialized equipment, and they still lose muscle mass. After 6 months in space, they struggle to walk when they return to Earth. Your bones deteriorate. Without the mechanical stress of gravity, your body decides it doesn't need as much bone mass. It starts reabsorbing calcium. Astronauts lose about 1 to 2% of their bone density per month in space. A 6-month journey to Mars, plus 18 months on Mars, which has only 38% of Earth's gravity, plus 6 months back. You're looking at severe osteoporosis. Bones so weak they could fracture under normal stress. Your cardiovascular system changes. Your heart doesn't have to work as hard to pump blood upward against gravity. It gets lazy. The fluid in your body redistributes, shifting toward your head. Your face puffs up, your legs thin out, and your cardiovascular fitness declines even with exercise. Your eyesight deteriorates. This is a relatively recent discovery and particularly concerning. Many astronauts returning from long-duration spaceflight have experienced vision problems. The leading theory is that increased intracranial pressure, caused by fluid redistribution, presses on the optic nerve. Some astronauts have come back needing glasses who had perfect vision before. Some have permanent damage. Your immune system weakens. Studies show that the immune response is suppressed in space. Latent viruses can reactivate. Wound healing is impaired. The ability to fight infection is reduced. On a long mission, this could be catastrophic. A minor infection that would be trivial on Earth could become life-threatening in space. And radiation, which we've already discussed. It's damaging your cells every day. Your DNA is accumulating mutations. Your cancer risk is climbing. Your brain is being slowly degraded by heavy ions passing through your neurons. So by the time astronauts reach Mars, they're not in peak condition. They're weakened. Their muscles have atrophied despite exercise. Their bones are fragile. Their cardiovascular systems are deconditioned. Their immune systems are suppressed. Their eyes might be damaged. Their cognitive function might be impaired. And now they have to land on Mars and immediately start working. Physically demanding work, setting up habitats, unloading equipment, conducting research. All in spacesuits that weigh over 100 pounds in Earth terms, though less in Mars gravity. All on a planet they've never experienced, with no margin for error. If someone breaks a bone, there's no hospital. If someone has a heart attack, there's no emergency room. If someone has a psychological breakdown, there's no facility to help them. The crew is the hospital. The crew is everything. And the crew is already compromised by months of spaceflight. This is not a theoretical concern. NASA and other space agencies are genuinely worried about it. They're researching countermeasures. Artificial gravity, perhaps generated by spinning the spacecraft or part of it. Better exercise protocols. Pharmaceutical interventions. But none of these are solved problems. None of them are ready for deployment. The current plan, if you can call it a plan, is to just accept the degradation and hope astronauts can still function when they arrive. Hope is not an engineering solution. And then there's the landing itself. Landing on Mars is incredibly difficult, much harder than landing on the Moon. The Moon has no atmosphere, so you can use rockets to slow down all the way to the surface. Simple in concept, though still technically challenging. Mars has an atmosphere, but it's the worst of both worlds. Too thin to slow you down enough, too thick to ignore. When spacecraft enter the Martian atmosphere, they're traveling at about 12,000 miles per hour. The atmosphere provides some braking. Heat shields and parachutes can slow you down to maybe a few hundred miles per hour. But that's still way too fast to land safely. And parachutes don't work well in the thin Martian air, especially for heavy payloads. For the final descent, you need rockets, retro rockets that fire to slow you down those last few hundred miles per hour. This requires fuel, which adds weight, which makes the rocket equation even more punishing. The heaviest thing we've ever landed on Mars is the Curiosity rover. 1 ton, just over 2,000 pounds. It required an incredibly complex landing system, a heat shield, a supersonic parachute, and then a sky crane that lowered the rover on cables while hovering on rockets. A crewed Mars mission would need to land payloads of 20 to 40 tons. That's 1 to 2 orders of magnitude heavier than anything we've ever landed on Mars. And we don't know how to do it. NASA has studied the problem. They've come up with concepts. Inflatable heat shields that increase drag, supersonic retropropulsion, using rockets that fire while the spacecraft is still moving supersonically, larger parachutes, different entry trajectories. But none of these have been tested at scale. None of them are proven technologies. They're concepts, ideas, possibilities, not solutions. The margin for error is 0. If the heat shield fails, the spacecraft burns up. If the parachute fails, the spacecraft crashes. If the retro rockets malfunction, the spacecraft crashes. There's no abort mode. Once you're committed to entry, you're committed. You either land successfully or you die. With robotic missions, we accept some failure rate. Mars has a history of failed missions, spacecraft that crashed, that missed the planet, that failed on landing. For robots, that's acceptable risk. For humans, it's not. So we need landing systems that are not just functional, but essentially perfect. Systems with reliability approaching 100%. And we've never demonstrated that kind of reliability for large payloads on Mars. Let's also talk about communication during landing. The entry, descent, and landing phase, EDL, is often called the 7 minutes of terror. It takes about 7 minutes from atmospheric entry to touchdown, and during much of that time, communication is difficult or impossible due to plasma blackout and the spacecraft's orientation. For crewed missions, the astronauts would be on their own during the most dangerous phase of the mission. No help from Earth. The signal delay means that by the time mission control sees a problem, it's already been resolved one way or another. The astronauts would have to trust the automated systems, or they'd have to be able to take manual control, which introduces its own risks. Human error under extreme stress, inadequate situational awareness, reaction time limitations. And this assumes the astronauts are in good cognitive shape. After 6 months of radiation exposure and the physical stresses of spaceflight, they might not be. Studies have shown that astronauts returning from long missions have measurable cognitive impairment. Decision-making is slower. Working memory is reduced. Under the extreme stress of EDL, this could be catastrophic. So let's add it up. 6 months in a tin can, exposed to radiation, muscles atrophying, bones weakening, immune system failing, eyesight degrading, then the most dangerous landing ever attempted, on a planet that will kill you if anything goes wrong. Then 18 months on, an alien world, isolated, cramped, with limited supplies, and no possibility of rescue. Then 6 more months of spaceflight with all the same problems, ending with a high-speed re-entry into Earth's atmosphere. Each phase of this mission has serious, potentially unsolvable problems, and the phases are sequential. You have to survive all of them. A failure at any point is potentially fatal. This isn't pessimism. This is physics. This is biology. This is the honest assessment of the challenge. And yet, we hear promises. 2030, 2040. Soon, just a matter of funding and political will, as if the problems are merely administrative, as if we've already solved the physics and we're just waiting for the check to clear. We haven't solved the physics. We haven't solved the biology. We haven't solved the engineering. And I don't know when we will. But let's keep going, because we haven't even talked about the hardest part yet, the part that might make everything else irrelevant, the fuel problem. The fuel problem is the problem. It's the constraint that makes everything else harder. And it's not an engineering problem. It's a physics problem. It comes directly from the laws of nature, and no amount of cleverness can make it go away. I want to explain this carefully because it's the key to understanding why Mars is so hard. If you understand the fuel problem, everything else makes sense. If you don't, you'll think the challenges are just a matter of trying harder. Let's start with the basic physics. A rocket works by throwing mass out of the back end. That's it. That's the only way to change velocity in space. There's nothing to push against. No road, no air, no water. You move by throwing stuff backward, and conservation of momentum pushes you forward. The efficiency of a rocket is measured by something called specific impulse, abbreviated ISP. It's basically how much thrust you get per unit of fuel. The higher the specific impulse, the more efficient the rocket. Chemical rockets, the kind we use today, have specific impulse values of about 300 to 450 seconds. That might not mean anything to you, so let me translate. It means that to change your velocity by a certain amount, you need to burn a certain fraction of your total mass as fuel. For a Mars mission using chemical rockets, the velocity changes required are so large that you need a truly staggering amount of fuel. Let's run some numbers. To escape Earth's gravity and enter a transfer orbit to Mars, you need about 4.3 kilometers per second of velocity change. To enter orbit around Mars, you need to slow down by about 2.4 kilometers per second. To land on Mars, another 1 kilometer per second or so, depending on how you do it. To take off from Mars and enter orbit, about 4.1 kilometers per second. To leave Mars orbit and enter a transfer orbit back to Earth, about 4 kilometers per second. To enter Earth orbit or aerobrake to landing, another couple of kms. Total it up, and you're looking at roughly 15 to 20 kilometers per second of velocity change for a round trip. Maybe more if things don't go optimally. Now, plug that into the rocket equation. The equation is exponential. That's the brutal part. It's not linear. Doubling the velocity change doesn't double the fuel requirement. It squares it. Or more precisely, it increases it exponentially. For a velocity change of 15 kilometers per second with chemical rockets, the fuel fraction required is extreme. You'd need something like 90 to 95% of your initial mass to be fuel. The spacecraft itself, including crew, life support, supplies, everything, would be 5 to 10%, maybe less. This is why the Saturn V was so massive. It was mostly fuel. And the Saturn V was designed for the Moon, which requires less than half the velocity change of a Mars round trip. Now, you might think, okay, we just build a bigger rocket, more fuel, more thrust, bigger vehicle. And yes, that's the obvious approach. But there are limits. The bigger the rocket, the heavier it is. And the heavier it is, the more fuel you need to lift it. The rocket equation applies to itself. You need fuel to lift the fuel. There's a point where adding more fuel doesn't help because the additional fuel adds more mass than it provides capability. This is called the tyranny of the rocket equation. And it's not a metaphor. It's a mathematical reality that limits what chemical rockets can do. For Mars, we're pushing up against those limits. The spacecraft required for a crewed Mars mission using chemical propulsion would need to be assembled in orbit. It would be too heavy to launch in one piece. You'd need multiple launches, orbital assembly, fuel transfers, all of which add complexity, cost, and risk. And even then, you'd be cutting it close. The margins would be thin, not much room for error, not much redundancy. Every kilogram would be accounted for. Every system would need to work perfectly. This is not how you want to run a mission where lives depend on the outcome. So what's the alternative? Better propulsion, higher specific impulse, getting more thrust per unit of fuel. The most promising alternative is nuclear propulsion. There are two main types, nuclear thermal and nuclear electric. Nuclear thermal rockets heat a propellant, usually hydrogen, using a nuclear reactor, and expel it out the nozzle. The specific impulse is about twice that of chemical rockets. 800 to 900 seconds instead of 400 to 450. That's a significant improvement. It means less fuel for the same velocity change, or more capability for the same fuel. Nuclear thermal propulsion was actually tested in the 1,960 seconds and early 1,970 seconds. The NERVA program demonstrated working nuclear rocket engines. Then the program was cancelled. Since then, there's been some renewed interest, but no flight-ready engines have been built. The challenges are significant. You're putting a nuclear reactor on a rocket. If the rocket explodes on launch, you've scattered radioactive material over a wide area. There are safety concerns, regulatory hurdles, public perception problems, and the engineering challenges of building a compact, reliable, high-performance nuclear reactor are not trivial. Nuclear electric propulsion is another option. Instead of heating propellant directly, you use a nuclear reactor to generate electricity, then use that electricity to accelerate ions in an electric thruster. The specific impulse can be very high, or 3,000 to 10,000 seconds or more, far more efficient than chemical or nuclear thermal. But there's a catch. Electric thrusters have low thrust, very low. They're efficient, but they accelerate slowly. A nuclear electric spacecraft might take months or years to build up speed. You can't use it for quick maneuvers or landing. It's only good for the long, slow cruise phase of the mission. So, the ideal scenario might be a combination. Nuclear electric for the transit, to maximize efficiency. Nuclear thermal, or chemical, for the maneuvers that require higher thrust. Landing, takeoff, orbit insertion. But this adds complexity. Multiple propulsion systems, multiple fuel types, more things that can break, more mass, more cost. And we still haven't built a flight-ready nuclear thermal rocket, let alone an integrated multimode system. There's another idea that gets floated. In situ resource utilization, ISRU. The concept is to manufacture fuel on Mars using local resources, so you don't have to bring all the fuel from Earth. Mars has carbon dioxide in its atmosphere, a lot of it, and there's water ice below the surface and at the poles. Using the Sabatier reaction, you can combine carbon dioxide and water to produce methane and oxygen, both of which are rocket propellants. This is the basis for SpaceX's Starship architecture. The idea is to land on Mars, set up a fuel production facility, and make the return fuel on site. That way, you only have to bring fuel for the outbound trip and the landing. The return trip is fueled locally. It's clever. It reduces the mass you have to launch from Earth by a significant factor. It makes the mission more feasible. But it's not easy. Making fuel on Mars requires power, a lot of power. The Sabatier reaction doesn't run itself. You need energy to harvest carbon dioxide, mine and melt ice, and drive the chemical processes. On Mars, that means either solar power or nuclear power. Solar power on Mars is about 40% as strong as on Earth, because Mars is farther from the sun. Dust storms can reduce it further. You'd need large solar arrays, which add mass. And during a global dust storm, which can last months, you might not have enough power to run your fuel plant. Nuclear power is more reliable but heavier and more complex. You'd need to land a nuclear reactor on Mars, set it up, and operate it for months or years. This is doable in principle, but it's never been done. And here's the thing. The fuel production has to work before you can leave. If the ISRU system fails, if it doesn't produce enough fuel, you're stranded on a planet that will kill you eventually, with no way home. You could bring backup fuel, but that defeats the purpose. The whole point of ISRU is to reduce the fuel you need to bring. If you bring enough backup fuel to return without ISRU, you've just massively increased the mission mass and cost. So ISRU is not just a nice to have, it's a mission-critical dependency. The entire return strategy relies on manufacturing fuel in an alien environment with equipment that's never been tested at scale. If it doesn't work, people die. This is the kind of thing that engineers lose sleep over. Single points of failure in life-critical systems, dependencies on unproven technologies, situations where there's no backup plan. Now, let's talk about another fuel-related problem. The fuel has to last. Chemical propellants, particularly the liquid hydrogen often used for high-performance rockets, are difficult to store. Liquid hydrogen boils at 20 Kelvin, just 20 degrees above absolute zero. It's constantly trying to evaporate. Over a multi-month journey, significant fuel can be lost to boil off. This is called cryogenic storage, and it's a hard problem in space. You need insulation, cooling systems, and strategies to manage the inevitable loss. The longer the mission, the more fuel you lose. For a 6-month transit to Mars, plus 18 months on the surface, plus 6 months back, you're looking at over 2 years of fuel storage. Even with advanced insulation and zero boil-off technologies, this is challenging. And we haven't demonstrated long-term cryogenic storage in space at the scale required for a Mars mission. SpaceX's Starship uses methane and oxygen, which are easier to store than hydrogen. That's one advantage of their approach. But even those propellants need to be kept cold, and Mars is a harsh environment for any machinery. So here's where we are with the fuel problem. Chemical rockets are barely adequate, pushing the limits of the rocket equation, requiring massive spacecraft with thin margins. Nuclear propulsion could help, but isn't flight-ready and has serious practical challenges. ISRU could reduce the fuel burden, but introduces critical dependencies on unproven systems. And all of this has to work reliably for years in the harsh environment of space and Mars. This isn't a matter of funding, it's not a matter of political will, it's physics and engineering. The problems are real, and the solutions don't exist yet. But let's assume we solve the fuel problem. Let's assume nuclear propulsion works. Let's assume ISRU works. Let's assume we can get there and back without running out of fuel. We still have the problem of surviving on Mars itself, and that's where things get even more complicated. The surface of Mars is, without exaggeration, one of the most hostile environments in the solar system for human life. Not the most hostile. Venus is worse. Jupiter's moons are worse. The surface of Mercury is worse. But Mars is bad enough that survival requires constant, active technological intervention. Let's go through it systematically. First, the atmosphere. I mentioned this before, but let me emphasize it. The atmospheric pressure on Mars is about 0.6% of Earth's. At that pressure, you cannot survive without a pressure suit or a pressurized habitat. Your body requires pressure to function. Without it, blood boils, tissues swell, and death occurs within seconds. So every moment on Mars outside a habitat, you're in a spacesuit. And spacesuits are not comfortable. They're bulky, restrictive, and require significant physical effort to operate in. The Apollo astronauts were exhausted after lunar EVAs. Mars EVAs would be longer, more frequent, and more demanding. Suit failures are possible. A tear, a seal failure, a helmet crack, any of these could be fatal. On Earth, astronauts train for suit failures, but the training assumes rapid access to a pressurized environment. On Mars, you might be kilometers from your habitat. A suit failure could mean death before you get back. Second, the temperature. Mars is cold, really cold. The average temperature is about minus 60 degrees Celsius, minus 80 Fahrenheit. At night, it can drop to minus 100 Celsius or lower. During the day, at certain locations and times, it might get close to freezing, but never warm, never comfortable. Heating is essential. Habitats need to be heated continuously. Suits need to be heated. Equipment needs to be protected from thermal stress. All of this requires power, which brings us back to the energy problem. Third, the radiation. We talked about this in the context of the transit, but Mars doesn't help. Mars has no global magnetic field. It lost its field billions of years ago, and the lack of magnetic protection means the surface is constantly bombarded by solar radiation and cosmic rays. The thin atmosphere provides some shielding, but not much. The surface radiation dose on Mars is estimated to be about 0.67 millisieverts per day. That's about 10 times higher than the average exposure on Earth. Over 18 months on the surface, astronauts would receive a significant radiation dose, adding to what they accumulated during transit. Habitats would need to provide radiation shielding. Underground habitats, or habitats covered with regolith, Martian soil, could help. But building those requires equipment and time. Initial surface operations would be exposed. Fourth, the dust. Martian dust is not like Earth dust. It's fine, abrasive, and potentially toxic. It gets everywhere, into seals, into machinery, onto surfaces. The Apollo astronauts had significant problems with lunar dust, and Mars dust is arguably worse. The perchlorates in Martian soil, which I mentioned earlier, are a particular concern. These chemicals are harmful to humans. They interfere with thyroid function. Exposure would need to be carefully managed. Any dust that gets into habitats would be a health hazard. Fifth, the communications delay. We talked about this in terms of psychological isolation, but it has practical implications too. If something goes wrong on Mars, you can't call Houston and get an immediate answer. You send a message, wait 10 to 40 minutes for a response, and then respond to that. For time-critical problems, you're on your own. This changes everything about how you operate. Procedures can't rely on real-time support from Earth. Astronauts need to be capable of solving problems independently, with whatever resources they have. Training needs to be comprehensive. Redundancy needs to be extreme. There's no helpline. 6. The medical challenges. Astronauts on Mars could get sick or injured. Heart attacks, strokes, appendicitis, broken bones, cuts, infections. All the things that can go wrong with the human body. On Earth, we have hospitals, doctors, specialists, equipment. On Mars, you have what you brought. The medical capability of a Mars mission would be limited by mass constraints. You can't bring an MRI machine or a surgical suite. You'd have basic supplies, some diagnostic equipment, and whatever medical training the crew has. If someone needs surgery, the crew performs it. Probably someone with minimal surgical training, using limited equipment, in partial gravity, with a communications delay to any expert advice. The outcome statistics for such procedures would not be encouraging. Some conditions would simply be untreatable. A severe trauma, a stroke, a major organ failure, the patient would die. There's no way around that. It's the price of isolation. So that's Mars, a frozen, irradiated, toxic, isolated wasteland where every moment requires active intervention to survive. Where a single failure, a suit breach, a habitat leak, a medical emergency could be fatal. Where help is months away, even if it were possible at all. And people want to colonize this place, build cities, raise children, create a backup civilization. I'm not saying it can never happen. I've been doing physics long enough to know that never is a dangerous word. But I am saying it's not going to happen the way the optimists think. It's not a matter of Elon Musk writing a check and sending rockets. It's a matter of solving problems we don't yet know how to solve. Decades of work, maybe centuries. The physics doesn't lie. The biology doesn't lie. Mars is hard in ways that Earth has never been hard, and wishing it were easier doesn't make it so. Let me tell you a story about complexity. Because one of the things people underestimate most about Mars is how all the problems interact. It's not just radiation. It's not just the rocket equation. It's not just the landing or the surface conditions. It's all of them, simultaneously, for years, with no room for error. In engineering, we talk about systems. A spacecraft is a system. It has subsystems: propulsion, power, life support, communications, thermal control, structural. Each subsystem has components. Each component has failure modes. And the interactions between subsystems create emergent failure modes that you might not anticipate when designing each subsystem in isolation. A Mars mission would be the most complex system ever built. Not by a little, by a lot. The space shuttle was the most complex flying machine ever built, with about 2.5 million parts. A Mars spacecraft, with its habitat modules, propulsion systems, ISRU equipment, landing systems, surface vehicles, spacesuits, and everything else, would be far more complex. And here's the thing about complex systems: they fail. It's not a matter of if, it's when. No matter how carefully you design, how thoroughly you test, how many backups you include, something will go wrong. The question is whether you can recover. On Earth, when something goes wrong, you can usually recover. You have resources. You have backup options. You can improvise. You can call for help. On Mars, your options are limited. What you have is what you have. If a critical system fails and you don't have a spare or a way to repair it, you're in trouble. Maybe fatal trouble. Let me give you an example. Life support. Life support is the system that keeps you alive. It provides oxygen, removes carbon dioxide, manages temperature and humidity, recycles water, processes waste. On the ISS, life support is a complex, heavy, power-hungry system that requires regular maintenance and occasional resupply from Earth. For a Mars mission, life support has to work reliably for 3 years with no resupply. Every component has to last, and if something breaks, you have to fix it with what you have. The most critical function is carbon dioxide removal. Humans exhale CO2 constantly. If it builds up in the atmosphere, it's toxic. Concentrations above, about 3%, cause headaches, dizziness, confusion. Above 8%, you lose consciousness. Above 10%, you die. On the ISS, CO2 is removed using lithium hydroxide canisters and a system called the carbon dioxide removal assembly. The canisters need to be replaced. The CDRA needs maintenance. Parts fail. Things go wrong. During Apollo 13, CO2 removal became a crisis. The explosion damaged systems, and the astronauts had to improvise a fix using duct tape and cardboard to adapt lithium hydroxide canisters from the command module to work in the lunar module. It was a brilliant piece of improvisation, and it worked. But it only had to work for a few days. On Mars, a CO2 removal crisis would have to be managed for weeks or months, not days. You'd need to repair or replace the system permanently. If you couldn't, you'd slowly suffocate. And CO2 is just one thing. What about oxygen generation, water recycling, waste processing, thermal control, power generation? Each of these systems has failure modes. Each of them has components that wear out. Each of them is critical. The ISS has redundancy, multiple systems that can take over if one fails. But redundancy adds mass, and mass is the enemy of Mars missions. Every redundant system you bring is mass that has to be accelerated out of Earth orbit, decelerated at Mars, landed on the surface, and potentially lifted back off again. So you have a tension. You want redundancy for safety, but you need to minimize mass for feasibility. The optimal point is somewhere in between, and finding it is extraordinarily difficult. And remember, the systems don't exist in isolation. If the power system fails, everything fails. No power means no life support, no communications, no thermal control. You'd have hours to fix it before the habitat became uninhabitable. If the water recycling system fails, you start depleting your reserves. You have some backup water, but not enough for years. If you can't fix the recycling, you ration. You get dehydrated. Your physical and cognitive performance degrades. Other problems get harder to solve. If the thermal control system fails, the habitat either freezes or overheats. On Mars, where the outside temperature is minus 60 Celsius on average, losing heat means death. Your systems start failing. Pipes freeze. Equipment malfunctions. People die. This is what I mean by interactions. A failure in one system cascades to others. A power failure causes a thermal failure, causes a life support failure. The systems are coupled. You can't separate them. And the longer the mission, the more likely failures become. Components wear out. Seals degrade. Lubricants fail. Electronics accumulate radiation damage. The probability of something breaking increases with time. And a Mars mission is a long time. On the ISS, systems are replenished and maintained with regular resupply missions. Critical components are swapped out before they fail. The station is essentially rebuilt continually, piece by piece, to keep it operational. Mars has no resupply. What you launch with is what you have, for 3 years. If you didn't bring a spare, you don't have a spare. If you didn't anticipate a failure mode, you can't fix it. This drives mission planners crazy. You have to anticipate everything, every failure mode, every combination of failures, every cascade. And you can't anticipate everything. Something will be missed. Something will fail that you didn't expect. The history of spaceflight is full of surprises, problems that no one anticipated, anomalies that shouldn't have happened, hardware that failed in ways the designers never imagined. Apollo 13 is the famous example, but there are many others. The Hubble Space Telescope launched with a flawed mirror because of a testing error. The Mars Climate Orbiter was lost because of a unit conversion mistake. The Challenger exploded because O-rings failed in cold weather, a failure mode that was known but inadequately addressed. Columbia broke apart because foam insulation damaged the heat shield during launch. Each of these involved complex systems, where unexpected failures occurred, despite rigorous testing and design. Each of them involved interactions that were missed or underestimated. A Mars mission would be more complex than any of these. It would operate for longer. It would be farther from help. And the consequences of failure would be more severe. I'm not saying we shouldn't try. I'm saying we should be honest about the difficulty. The casual optimism that surrounds Mars discussion, the idea that it's just a matter of willpower and money, is dangerous. It leads to bad decisions. It leads to inadequate preparation. It leads to tragedies. Let me talk about another kind of complexity, human complexity. A Mars mission isn't just a hardware problem. It's a human problem. People have to operate the systems. People have to make decisions. People have to work together under extreme stress for years. Human factors engineering is a discipline devoted to designing systems that humans can operate effectively. It's harder than it sounds. People make mistakes, people get tired, people get confused. People have emotional reactions that affect their judgment. On a Mars mission, the crew would be making critical decisions every day. How to prioritize tasks, how to allocate resources, how to respond to anomalies. Every decision has consequences. Some decisions are irreversible. The crew would have to be extraordinarily competent, not just technically competent, but socially competent. They'd have to work together, support each other, resolve conflicts, maintain morale. For 3 years, in a tin can, under constant stress. Studies of isolated groups show that conflict is almost inevitable. Personality clashes, power struggles, in-group, out-group dynamics. Even highly trained, carefully selected people eventually have problems. The most successful isolated groups have strong leadership, clear roles, and effective conflict resolution mechanisms. But these are hard to maintain over long periods. Leadership can become authoritarian or ineffective. Roles can become contested. Conflicts can fester. And what happens if someone can't perform? If someone becomes psychologically incapacitated? If someone needs to be relieved of duty? There's no replacement crew. There's no way to send someone home. You have to manage with what you have. There have been incidents in isolated environments where people have had to be physically restrained, where violence occurred, where people became so dysfunctional that the mission was compromised. We'd like to think astronauts are above this. They're selected for stability. They're trained for teamwork. They're professionals. But they're human. And humans break under enough stress. NASA has conducted studies on long-duration isolation. They've run simulations where crews live in isolated habitats for months. The results are concerning. Even in simulations, where participants know they can leave if necessary, conflict and psychological problems emerge. A real Mars mission, where there's no exit, where the stakes are life and death, would be far more stressful. We simply don't know how people would respond, and we can't fully simulate it. The only way to find out is to try it, and trying it with lives on the line is not an experiment anyone should take lightly. Let me also mention something that's often overlooked, the ethical dimension. Sending people to Mars is not like sending them to the moon. The moon is 3 days away. If something goes wrong, there's a chance of rescue. Apollo 13 proved that. The astronauts were in danger, but they were also in reach. Earth could help. Mars is 6 months away at minimum. If something goes wrong, there's no rescue, no chance. The astronauts would die, and we would watch it happen, helplessly, from 140 million miles away. Is it ethical to send people on a mission like that? To ask them to accept risks that far exceed any previous spaceflight? To know, going in, that if certain things go wrong, they will die, and no one can save them? The astronauts would volunteer, of course. They'd accept the risks knowingly. But does that make it ethical? We don't let people consent to certain risks even if they want to. We have safety regulations, liability laws, ethical oversight. Some would argue that exploration has always involved risk, that the explorers who crossed oceans, climbed mountains, charted unknown territories, also faced death. That accepting such risks is noble, even heroic. And that's true, but there's a difference between risk you can manage and risk you can't. The early explorers could sometimes turn back, sometimes get rescued, sometimes find unexpected resources. A Mars mission has none of those options. The risk is more absolute. I don't have a simple answer to this. I'm not saying we should never take such risks, but I am saying we should take them seriously. We should think carefully about what we're asking people to do. We should be honest about the dangers. We should not send people to die for marketing purposes or political stunts. The history of exploration is full of deaths, many of them unnecessary, many of them caused by inadequate preparation, overconfidence, or willful blindness to risks. Let's not add to that history. And let me mention one more thing: the financial complexity. A Mars mission would cost a lot of money. Estimates vary, but we're talking hundreds of billions of dollars at minimum. Some estimates go to $1 trillion or more, and that's just for one mission. A single round trip, not a colony, not a permanent presence, just getting there, and back. For context, the entire Apollo program cost about $25 billion in 1,960 seconds money. That's about 200 billion in today's dollars. And Apollo was a massive national effort at the peak of Cold War motivation. A Mars mission would cost more, possibly much more. And we don't have Cold War motivation. We don't have the sense of existential competition that drove Apollo. We have billionaires who want to go to Mars, but even the richest billionaires can't fund a program at this scale. So funding would have to come from governments, and governments have many priorities: healthcare, education, infrastructure, defense. Space exploration is a small fraction of any national budget. Sustaining a multi-decade program of this magnitude would require extraordinary political commitment. Political commitment is notoriously unstable. Administrations change, priorities shift. The same Congress that approves funding one year can cut it the next. Long-term programs are constantly at risk of cancellation. NASA has experienced this repeatedly. Programs started with great fanfare, then canceled before completion. Constellation, the Space Exploration Initiative, others. Mars programs are particularly vulnerable because the timeline is so long. By the time you're ready to launch, the political landscape has changed multiple times. This is not a criticism of any political party or philosophy. It's just how democracies work, and it's a fundamental obstacle to a Mars mission. The program would need to be sustained across decades through multiple administrations, multiple Congresses, multiple shifts in public opinion. I'm not sure that's possible. Not in the current political environment. Maybe I'm wrong. Maybe Mars will capture the imagination in a way that transcends politics. But history suggests otherwise. History suggests that big, expensive, long-term programs get canceled more often than they get completed. So even if we solve the physics, even if we solve the engineering, even if we solve the human factors, we still have the funding problem, the political problem, the societal problem. Mars is hard in every dimension. Not just technically, not just physically, but economically, politically, ethically. Every dimension you examine reveals new difficulties. And yet, people keep working on it. NASA has plans. SpaceX has plans. China has plans. Something in us wants to go. Something in us refuses to accept limits. Maybe that's the best argument for trying. Not that it's easy, not that success is assured, but that the challenge itself is worthwhile, that pushing against limits is what humans do, that we'd rather fail reaching for Mars than succeed at staying home. I'm not sure. I genuinely don't know whether a Mars mission is worth the cost and risk, but I do think the conversation needs to be honest. We need to understand what we're talking about. Not the fantasy version, not the marketing version, the real version. And the real version is hard, possibly impossible with current knowledge, certainly not happening in the timelines people casually mention. But maybe that's okay. Maybe the goal isn't to get there next year or next decade. Maybe the goal is to get there eventually, to keep working, to keep learning, to solve one problem at a time until someday we're ready. That's a humbler vision, less dramatic than the TED Talk version, but maybe more realistic, maybe more honest, maybe more worthy of what Mars actually is. A world, another world, a place that exists whether we go there or not, a place that doesn't care about our ambitions or our timelines, a place that simply is, waiting, patient, indifferent. If we ever get there, it won't be because we wanted it badly enough. It will be because we solved the problems, because we did the work, because we faced the physics and found answers. And maybe we will. Humans are clever. We've done hard things before. We've achieved what seemed impossible, but not by pretending it was easy, not by wishing the problems away, not by marketing ourselves past the difficulties. By working, by thinking, by being honest about what we don't know. That's how we got to the moon. That's how we'll get to Mars, if we ever do. Let me tell you something that very few people want to hear. The reason we went to the moon in 1969 is not the reason people think. And the reason we haven't gone back, the reason we haven't gone to Mars, is not the reason people think either. The common story goes like this. We went to the moon because humans are explorers, because we have an innate drive to push boundaries, because it was the next frontier, and we couldn't resist. We haven't been back because we've been waiting, building up, preparing for the next leap. That's a nice story. It makes us feel good about ourselves. But it's not true. We went to the moon because of the Cold War. Pure and simple. The United States and the Soviet Union were locked in an existential struggle, and space became a proxy battlefield. When the Soviets launched Sputnik, when they put Gagarin in orbit, America felt threatened, not just embarrassed, threatened. It was a national security issue. Kennedy didn't announce the moon program because he loved science. He announced it because he needed a win. He needed something big, something dramatic, something that would prove American superiority. Landing on the moon was the most ambitious thing he could think of that the Soviets hadn't already done. The money flowed. Not because Congress loved exploration, but because Congress was scared. Scared of falling behind, scared of losing the technological race that would determine military dominance. NASA's budget peaked at over 4% of federal spending. That's extraordinary. Today, it's about 0.5%. And when we won, when we planted the flag and came home, the motivation disappeared. The Soviets weren't going to the moon. The race was over. Why keep spending billions? Congress didn't see the point. The public lost interest. Apollo was canceled after 17, and we never went back. This is important to understand because it explains why Mars is so hard politically. There's no Cold War equivalent driving us to Mars. There's no existential threat that makes Mars urgent. There's no enemy we need to beat. China is developing a space program. Yes, they've put astronauts in orbit. They've landed on the moon's far side. They talk about Mars, but they're decades behind the US in most areas, and the geopolitical stakes aren't the same. The Cold War was an ideological struggle between two superpowers that controlled most of the world. The current competition with China is different in kind. More economic than ideological, less existential. Without that Cold War pressure, space exploration becomes optional. It competes with other priorities: healthcare, infrastructure, defense, climate change, all of which are more immediate, more tangible, more politically salient. Mars is important to some people, but it's not urgent to most voters. This is why NASA's budget has been flat for decades. This is why Mars programs keep getting delayed and deferred. This is why the timeline keeps slipping. It's not technical problems, though those are real. It's political will, or rather, the absence of it. Now, some people think private industry will change this. Elon Musk, Jeff Bezos, the new space billionaires. They have vision. They have resources. They don't need Congress. And it's true that SpaceX has accomplished remarkable things. They've revolutionized launch costs. They've demonstrated reusability. They've made space more accessible than it's ever been. But Mars is different. Mars is not a matter of reducing launch costs by a factor of 10. The challenges are more fundamental. The radiation, the landing, the surface operations, the return journey. These are not problems that get solved by iterating on rocket designs. SpaceX's current plan involves Starship, a giant reusable rocket that would serve as both the launch vehicle and the Mars lander. The architecture is clever. It relies heavily on ISRU for return fuel. It aims for high-frequency, high-volume missions that would eventually establish a colony. But Starship is still in development. Test flights have had mixed results. The timeline keeps slipping, and even if Starship works exactly as planned, it doesn't solve the fundamental problems I've been describing. It doesn't solve radiation. Starship provides no more radiation protection than any other spacecraft design. The crew would still be exposed for months. It doesn't solve the medical challenges. Astronauts would still arrive on Mars deconditioned and weakened. It doesn't solve the psychological challenges. Years of isolation in close quarters. It doesn't solve the surface operations challenges. A hostile planet is still hostile. SpaceX is solving the transportation problem. Getting mass from Earth to Mars orbit. That's valuable, that's necessary, but it's not sufficient. And the economics are still unclear. SpaceX is a for-profit company. Eventually, they need to make money. Who pays for Mars missions? NASA might contract some. Wealthy individuals might pay for seats. But a sustained colonization program? Where does that money come from? Musk talks about making Mars self-sustaining, a colony that can survive without support from Earth. But that's a goal that's decades away at minimum, assuming everything goes well. In the meantime, every mission requires billions of dollars. Every resupply, every new habitat, every piece of equipment. The initial colonists would be entirely dependent on Earth for survival. One failed resupply, one missed launch window, and they're in trouble. Maybe fatal trouble. The colony can't be self-sustaining until it's very large, with diverse capabilities, with the ability to manufacture everything it needs locally. That's not a decade-long project. That's a century-long project. I'm not saying it can't happen. I'm saying the cheerful timelines you hear, cities on Mars by 2050, 1 million people by 2100, those don't match the engineering realities. They don't match the economic realities. They don't match the political realities. And there's something else, something nobody likes to talk about. The death rate. Early Mars missions will have a high failure rate. Maybe not the first mission, if we're cautious and lucky, but as missions accumulate, as systems age, as complexity grows, failures will happen. People will die. On the frontier, people die. That's always been true. The American West was settled at the cost of many lives. Exploration always has casualties. But we live in a different era now. We have different expectations. When astronauts die, it's a national trauma. Challenger, Columbia, 7 people each time, and the entire country mourned. Spaceflight programs were suspended for years. How will we respond when Mars colonists die? When the death toll is not 7 but 70 or 700? Will public support survive? Will funding continue? Or will there be a backlash? Demands to end the program? Accusations of recklessness? I don't know, but I think the question needs to be asked. We're not psychologically prepared for the death rate that colonization requires. Our culture values safety in ways that previous frontier eras did not. That's not wrong. Human life is precious, but it might be incompatible with the Mars project as currently envisioned. Musk has said he expects people to die on Mars. He's been explicit about it. He's warned potential colonists that it will be dangerous. And that's honest, more honest than most Mars advocates. But saying it and living it are different things. When the first colonists die on live television, beamed back from Mars with a 20-minute delay, watched by millions, the reaction might not be what Mars advocates hope. It might not be brave pioneers accepting risk. It might be billionaires' vanity project kills desperate people. The narrative matters. Public perception matters. And public perception is unpredictable. Let me talk about something more fundamental. The question of why. Why go to Mars? What's the point? There are several answers people give. Let me go through them. Science. Mars is scientifically interesting. It might harbor evidence of past life. It can teach us about planetary geology, atmospheric dynamics, solar system, history. These are legitimate scientific goals. But here's the thing. Robots can do most of this science. They already are. Curiosity and Perseverance are doing excellent science on Mars right now, at a fraction of the cost of a human mission, without risking lives. Yes, humans can do some things robots can't. Humans are more flexible, more adaptive, better at recognizing unexpected finds. But the difference is not as great as people assume, and it's shrinking as robotic technology improves. If the goal is science, robotic missions offer far better value. More missions, more sites, more data, for less money, and no lives at risk. Survival of the species. The backup civilization argument. Earth could be hit by an asteroid. A supervolcano could erupt. A pandemic could kill everyone. Nuclear war. Climate catastrophe. We need a second location for humanity. This is the argument Musk makes most often. Mars as insurance policy. And it's a real argument. Species survival is a legitimate goal, but there are problems with it. First, Mars doesn't solve most existential risks. An asteroid that hits Earth doesn't threaten Mars. But a pandemic doesn't spread to Mars anyway. Nuclear war on Earth doesn't affect Mars. Most existential risks are Earth-specific. The risks that could threaten both planets, a nearby supernova, a gamma-ray burst, those are so rare and catastrophic that a Mars colony probably wouldn't help. You'd need colonies throughout the galaxy. Second, keeping a Mars colony alive without Earth support is extraordinarily difficult. We talked about this. The colony would need to be very large and very capable before it could survive independently. Until then, losing Earth means losing the colony. Third, the resources spent on Mars could be spent on other priorities. Climate change mitigation, asteroid defense systems, pandemic preparedness. These might reduce existential risk more effectively than a Mars colony, at lower cost. I'm not saying Mars is worthless as insurance. I'm saying the insurance argument is weaker than it appears when you examine it carefully. Inspiration, the human spirit, the drive to explore. This is the romantic argument. Going to Mars would be inspirational. It would capture the imagination. It would demonstrate what humans can achieve. It would encourage young people to study science and engineering. It would unite humanity in a common endeavor. Maybe. The moon landing was certainly inspirational. For those who were alive then, it was transformative, a defining moment. But the effect was temporary. Inspiration faded, interest waned, the moon became old news. By the late 1970s, most people couldn't name an astronaut. Would Mars be different? It might be more inspiring because it's so much harder, or it might be less inspiring because it's so far away and so slow. The moon landing was dramatic. A few days of tension, then triumph. A Mars mission would be months of nothing, interspersed with moments of crisis, not as televisual. An inspiration is hard to quantify, hard to justify in a budget hearing. Senator, we need $50 billion to inspire young people. That's not a winning argument. Finally, there's the economic argument. Resources, opportunities, a new frontier for economic growth. This is the weakest argument of all. Mars has no economically valuable resources that couldn't be obtained more cheaply on Earth or from asteroids. There's no trade that makes sense across 140 million miles. The transportation costs dwarf any conceivable profit. Maybe someday, far in the future, a self-sustaining Mars civilization could develop its own economy. But that's centuries away if it ever happens. The near-term economics of Mars are terrible. So why go? I'll tell you my answer. It's not scientific. It's not rational. It's not based on cost-benefit analysis. I think we should go because it would be magnificent. Because the universe is vast and mostly empty and hostile, and we're small and brief and fragile, and going anyway would be the most human thing we've ever done. Not practical, not sensible, not safe, just magnificent. But magnificence is not a policy argument. It won't convince Congress. It won't fund a program. It won't solve the engineering problems. So we're stuck. We want to go, but we don't want it badly enough to pay the price. We dream of Mars, but we're not willing to accept the risks and costs of actually getting there. Maybe that will change. Maybe something will shift in the culture, the politics, the technology. Maybe we'll find a way. Or maybe we won't. Maybe Mars will remain a dream, a beautiful, impossible dream that we tell ourselves stories about but never actually pursue. I don't know which future we'll get, but I want us to be honest about where we are now. We are not on the verge of going to Mars. We are not close. We are not almost ready. We are at the beginning, the very beginning, with most of the hard work still ahead, and no certainty that we'll ever finish. Let me tell you what I actually think. After all this, after the radiation and the rocket equation, and the landing, and the surface conditions, and the politics and the economics, what do I actually believe about Mars? I believe it's possible. Not easy, not soon, but possible. The physics doesn't forbid it. There's no law of nature that says humans can't go to Mars. It's hard, but hard things have been done before. We've solved problems that seemed impossible. Powered flight, splitting the atom, sending people to the moon, building computers that fit in your pocket. Problems that looked insurmountable until someone surmounted them. Maybe Mars is like that. Maybe we're at the stage where the problems look overwhelming because we haven't solved them yet. Maybe 50 years from now, people will look back and say, they actually thought it was impossible. How naive. I hope that's true. I really do. I'd love to be wrong about all of this. I'd love to see humans on Mars in my lifetime. It would be the greatest achievement in the history of our species. But hope isn't a plan. And right now, we don't have a plan. We have aspirations. We have concepts. We have PowerPoint presentations and artists' impressions and optimistic timelines. What we don't have is solutions to the actual problems. The radiation problem isn't solved. We don't have shielding that works against galactic cosmic rays. We don't have materials that stop them without creating secondary radiation. We have ideas, but not technologies. Not yet. The landing problem isn't solved. We've never landed anything close to the mass needed for a human mission. We have concepts, inflatable heat shields, supersonic retropropulsion, but we haven't demonstrated them. Not at scale, not in Mars conditions. The surface operations problem isn't solved. We don't know how to keep people alive for 18 months on Mars with the equipment we can realistically deliver. We have studies, but not systems. Not tested, validated, flight-ready systems. The return problem isn't solved. ISRU is a concept, not a capability. Making fuel on Mars requires infrastructure we've never built, power systems we've never deployed, processes we've never tested in actual Martian conditions. The human factors problems aren't solved. 3 years of isolation and confinement, crew dynamics under extreme stress, medical emergencies without hospitals, psychological degradation without support. We have data from analogs, but analogs aren't the real thing. So when someone says we're going to Mars in 2030 or 2040 or even 2050, I want to ask, which of these problems have you solved? Show me the hardware. Show me the test results. Show me the radiation data. Show me the mission simulations. Usually, the answer is that the problems will be solved in time. The schedule assumes breakthroughs. The plan relies on technologies that don't exist yet. That's not a plan. That's a prayer. Prayers sometimes get answered, but you shouldn't bet civilization on them. Now, let me be clear about what I'm not saying. I'm not saying we should give up. I'm not saying Mars is forever impossible. I'm not saying we should stop trying. What I'm saying is we should be honest. Honest about where we are. Honest about how far we have to go. Honest about the challenges that remain. Honesty isn't pessimism. Honesty is the foundation of progress. You can't solve problems you refuse to acknowledge. You can't fix things you pretend aren't broken. The worst thing we could do is pretend Mars is easy. Pretend the problems are mostly solved. Pretend we're almost ready, because that pretense leads to bad decisions, underfunded programs, unrealistic schedules, missions that fail because we weren't prepared. We need to take Mars seriously, not as a destination for the next decade, but as a multi-generational project, a 100-year program, something we start now, work on for our entire lives, and hand off to our children to continue. That's not exciting. It doesn't make for good press releases, it doesn't generate clicks or views or investment, but it might actually work. The cathedrals of medieval Europe took generations to build. The people who laid the foundations didn't live to see the spires completed, but they built anyway. They trusted that future generations would continue the work. Maybe Mars is like that. Maybe we're laying the foundations now, solving one problem at a time, developing one technology at a time, inching forward, decade by decade, until someday we're ready. That's a different kind of heroism than the astronaut's heroism, not the dramatic courage of risking your life on a dangerous mission. The patient courage of working on something you won't live to see completed, trusting that your contribution matters, even if you never witness the result. I find that inspiring in a different way, not the inspiration of a TED Talk. The quiet inspiration of persistence, of long-term thinking, of building for the future. Let me tell you what I'd like to see. I'd like to see sustained investment in research and development, not a crash program, not a race to a deadline, a steady, long-term commitment to solving the actual problems. Radiation shielding, advanced propulsion, life support systems, ISRU, landing technology, medical capabilities. I'd like to see robotic precursor missions, many of them, testing technologies on Mars, demonstrating ISRU, caching samples for return, mapping potential landing sites, building a foundation of knowledge before we send humans. I'd like to see orbital missions first. Humans going to Mars orbit, spending time there, returning home, getting experience with long-duration deep space travel, testing systems in realistic conditions, without the additional risks of surface operations. I'd like to see international cooperation. Mars is too big for one country, too expensive, too important. It should be a human project, not an American project or a Chinese project or a private company's project. All of humanity has a stake in this. I'd like to see honesty from NASA, from SpaceX, from everyone who talks about Mars. Honest timelines, honest assessments of risk, honest acknowledgement of what we don't know. Will any of this happen? I don't know. Politics is unpredictable. Funding is uncertain. Priorities change. The future is not ours to control. But I do know this. If we ever get to Mars, it will be because we did the work. Not because we wished hard enough. Not because we had a billionaire with a vision. Not because we were brave or bold or inspired. Because we solved the problems. Because we developed the technologies. because we tested and failed and learned and tried again, because we were patient and persistent and honest. That's how humans have always achieved hard things. Through work, through incremental progress, through the accumulation of small advances that eventually add up to something transformative. Maybe we'll get to Mars, maybe we won't. But if we do, it will be because of the people working today on problems that seem small. Radiation shielding materials, ion propulsion efficiency, life support recycling rates, problems that don't make headlines, problems that aren't sexy or exciting. Those are the heroes of Mars. Not the astronauts who will eventually make the journey. The engineers and scientists working now, today, on the boring problems that make the journey possible. Let me end with a thought about perspective. Mars is 140 million miles away. It's taken us 60 years to get from Sputnik to where we are today. 60 years of spaceflight, of incremental progress, of learning and improving. Maybe it will take another 60 years to get to Mars. Maybe 100. Maybe more. In the grand sweep of history, that's nothing. A blink, a heartbeat. We're a young species. We've been doing science for a few hundred years. Space travel for a few decades. We're just beginning to understand what's possible. Maybe Mars is the next step. Maybe it's the step after that. Maybe it's many steps away. But the direction is clear. Outward, into the cosmos. Because that's where everything is. The universe is unimaginably vast. It contains wonders we can't conceive of, places we can barely imagine, and we're trapped on this one small planet, looking up, wondering. Going to Mars wouldn't be the end. It would be the beginning, the first step on a journey that could last millions of years. A journey that could take us to other stars, other galaxies, across the cosmos. Or it could go nowhere. We could stay home, die on Earth, leave no trace in the universe, a species that briefly flickered and went out. I don't know which future we'll choose, but I know which one I hope for. I hope we choose the hard path, the path that leads outward, the path to Mars and beyond. Not because it's easy, because it's hard, because it's magnificent, because it's who we are or who we could be. That's my honest answer to the question of Mars. It's physically almost impossible. It's engineering almost impossible. It's economically almost impossible. Almost. And in that almost, there's room for hope, room for work, room for the future. I'm a physicist. I believe in evidence. I believe in honest assessment of reality. And my honest assessment is that Mars is one of the hardest things humans have ever contemplated. But I also believe in human ingenuity, in persistence, in the stubborn refusal to accept limits. We've done hard things before. We'll do hard things again. Maybe, someday, Mars